on this computer. All right, hello everybody, and I would like to start with saying, how was that exam? Okay, so I got some feedback from some of the students in the that had an SI session, and so I hope you weren't shocked by how the exam was laid out or how many questions it was or anything like that. I just finished grading all of the exams and setting the curve for this exam. The raw average was 60%. The scaled average is 74 point something, 74.5. So note that the number in the book is out of 120 points because I had to rescale the exams because Canvas doesn't let me just pick percentages. I have to pick points, and they all have to total up to something that gets a percentage. So that's why all the exams are actually 120 points, but there should also be a percentage column somewhere in there, and that's what the percent you got on there. We actually had 2 people that got scaled to 100% on this exam. So we have 2 people. So go ahead and look at those, and I have your homeworks in there. If something's wrong about that, go ahead and email me. I have to download 2 spreadsheets and cross them over and then eliminate people who weren't on both. So I may have had a little error on that, but please go ahead and check your exam grades and your homework to make sure all that's there. There's also a weird function in Canvas that I don't know why, but if things aren't graded, they count them as zeros. So your real grade is not necessarily the grade it's showing. I'm trying to figure out how to undo that so that it doesn't count things that aren't there. Also, I will be going ahead and doing the activity, going and grading the activity. I realized I didn't do that. It got kind of lost in Snowmageddon. So I will be doing that as well. Now, we also have an activity next week on chapter 5, which is what we're going to start today. So we'll be able to add to that activity score as well. So let's see how we're going. So right now the class overall is doing pretty good. I think the overall average in the class is a little less than 72, which is not bad for our first part of the semester. So we have plenty of time to work hard and do our homework and get a little bit higher grades. Also, it turns out that chapter 6 actually has 3 sections in it. So your total homework grade for that section, you do each of those for 20 points. So you get a total of 60 points for chapter 6. So you're actually going to get a little more, that's giving you extra points right there in the system. Okay, so that's going to be helpful for some of you as well. Okay, questions before we begin with chapter 5.
Were the group activities, the first one, were they graded?
I have not finished grading them, but I figured out how I can speed grade them on my iPad and make it really fast. But it's graded mostly for participation. So if you turn something in, you're going to get most of your points. Okay.
Dr. Irvin, I have a quick question. The Canvas deadline for the module 5 is different from Top Hat. Is the homework due this weekend?
The one on Top Hat is correct because I had to shift everything. I haven't finished shifting all of the Canvas stuff too. But the one with the updated schedule, if you click the updated schedule button, that is the most correct one. And those should be exactly the same as on Top Hat. Okay?
Okay, thank you.
So I am working on that. It's a lot of stuff to change in the middle of a semester, but I will get that corrected. Okay. So any other questions about the exam? Questions, comments, concerns? Okay. So I did actually, if you had looked at chapter 6, it wasn't open yet because I wanted to significantly change the slides from last year. So that's significantly changed and pared down. That kind of helps us because we are going, we lost 3 class days. And so that's going to help us catch up. So those are now available and open for review, and so we'll be getting to that in a second. So the grade you have on Top Hat is for the test is with no, Top Hat does weird calculations. Always go to Canvas. Canvas has the correct values. Okay. Now, if you have homework grades on Top Hat and you don't have them on Canvas, email me because there might have been something lost in translation. We will not have an opportunity to review the exam. I can review the topics. And what you should have seen in the exam is the questions are very similar to the homework, just changing structures. I'm trying to get you to, tell me that you understand the concept, not trying to trick you with the concept, okay? We have not done group activity 2. It is scheduled for next week under our new schedule, okay? Okay, so to some people, this is a very hard chapter, stereochemistry, okay? Now, but what I like to think is if you play a lot of Minecraft, this is really easy, okay? And I'm gonna show you a way to, number one, keep track of everything. Number two, how to use your hand to almost always get the right RNS configurations on your stereochemistry. And our activity will be RNS as well as E and Z assignments. So we're gonna kind of button this whole thing together with our activity, okay? So let me go ahead and switch iPad cables and start sharing my screen. Let's see, share my screen, there it is. Okay, now there it is. Yes, all right. So this module is up on Top Hat as well as also in Canvas. So if you want to download those and annotate as you go along, that's fine too. Preemptive strike with the green tea, so I won't start coughing again. Uh-oh. Cable move there. All right. Come on, come back. Bring window back to front. Stop share. Let me move my cable here. There we go. I'm going to stop share. I'm going to reshare, and everything should be back to normal. Okay, do you guys see my screen? Because I don't see my, okay, I don't see it either. Okay, let's try again. I saw it there for a minute. All right, let me swap cables here. I think that it might just be, it doesn't like the Apple cable. Let's see, does this solve my problem? Let me stop share and reshare again. All right, I still don't see it. Do you guys see it?
No.
Okay, let's try share with AirPlay. Screen mirroring David's iPad. It won't do that either. Interesting. Okay. Okay, that's interesting because it was just up there. We just saw it. So. Okay. All right, let's do it this way then. Stop share. Okay, my iPad does not want to share today, which is weird because it was just sharing 5 minutes ago. Let's see. Oh, you know what? I bet it's off screen because when I stop sharing, oh, there they are. Okay. All right, well, let me go ahead and pull something up on my, I think I have, all right, I'm gonna pull it up on my other computer. I can't believe it's admit. All right. Okay, so let me try to pull it up on Top Hat, and with it on Top Hat, I will present that way. Unfortunately, I won't be able to annotate for some reason. There we go. Yeah, we'll just have to do that. Sorry. Okay, stop share. Yay. Okay, yeah, let's try to restart the iPad here. I'll restart the iPad while we start the module, and then I can hopefully go back to it here. Stereochemistry. And present slides. Unassign and present while I'm on here. Start presentation. And now share my screen. Desktop. Share. Okay, do we see slides now? Yes, all right. All right, so I'm gonna reboot my iPad while we're talking here. So the whole point of stereochemistry is the fact that we have millions and millions of ways to hook these chemicals together, and sometimes we'll use the exact same atoms, but they're going to be hooked up differently. Okay, so in this term, stereochemistry has nothing to do with music or anything like that. It has to do with space. It's where they are fixed in space. Okay, so let's see if we can go ahead and go next. All right, so because we can have so many different compounds available to us, and sometimes they can have the exact same formula, but we know that we can hook them up to different ways, and we'll have different functional groups, and we'll have different properties that we can have. We'll have different interactions we can have, like we can have van der Waals forces versus dipole-dipole forces. So for example, something as simple as just 2 carbons, 6 hydrogens, and 1 oxygen can have 2 different isomers that have very different properties. For example, if we have 2 carbons hooked to our oxygen here, it doesn't hydrogen bond, and it only has those dipole-dipole interactions, and therefore it is a gas at room temperature. It is very, very volatile. It boils at like 13 degrees C, okay? However, just by rearranging a couple of those bonds and putting only 1 carbon to the oxygen and having a hydrogen available to hydrogen bond, that makes it allowed to have that higher energy interaction, that hydrogen bond, and it's actually a liquid at room temperature, and it boils at 78 degrees Celsius. Okay, so that's the effect of just having them hooked up in different directions. Okay, and okay, so I'm gonna stop share. I'm gonna hazard a guess and try to see if my iPad's gonna work because it's so much easier. Escape, and share with my iPad. Yes, all right. So we can see, can we see my iPad now? Okay, so, we have these different little isomers available to us, okay? So because they have different properties and they have different names, we have to pay attention to them. But within that group, we actually have a bunch of different things available to us, okay? So if we have just the same number of atoms, but hooked together differently, they're called isomers, okay? And so that's easy to think of, as iso meaning, shape, and mer meaning many, so many different shapes. There's several different types. One is called a structural or constitutional isomer. In the structural or constitutional isomer, those are how that they're hooked together. They have different types of bonds. They can have different types of functional groups, but they have all the exact same atoms. Okay, so that's what we call those structural or conformational isomers. The next type is where they're hooked together in exactly the same way, but there's something about them that changes where they are in space. Okay, so that's where the stereo comes in. It's basically just a change in space. So our stereoisomers are spatially different from each other, but connected exactly the same. Okay, so but within stereoisomers, if we have one stereocenter, you can have what's called a pair of enantiomers. So that's going to be two molecules that are identical in all of their structural characteristics and connections and physical properties, except that when you try to overlay them, two of the atoms have been swapped. Okay, and we're going to talk about that in detail. Now, if you have more than one stereocenter, you can now have diastereomers. And with diastereomers, those are going to be multiple sets of places on rearranging these groups in space. Okay, so the difference here is we're going to start with enantiomers, which is just a one stereocenter interaction, and then we'll move to diastereomers with two or more. Okay, and so let's go ahead and talk about constitutional isomers first. That's the easiest one to conceptualize because they're hooked together differently. And again, because they're hooked together differently, they'll have different interactions. When we talked about van der Waals forces, we said that things that were linear, the longer they were, they had stronger intermolecular forces because they could have more surface area attaching to them. And so our boiling point here is greatly affected by that. This is a little more spherical. It has fewer interactions with the molecules next to it by van der Waals forces or induced dipole forces. And therefore it has a lower boiling point. Notice part of that boiling point is just by the mass of the material. So the more atoms you add, your boiling point goes up. But then the next thing affects it is the type of interaction between the molecules. Okay, and we see that again when we are allowed to do hydrogen bonding. In this case here, the T-butanol here, because it has that long center, those van der Waals forces are more pronounced in that one, and we have a higher boiling point, even though they're all the same molecular weight and they all have a hydrogen bond. But by breaking up some of that van der Waals interaction, our boiling point can decrease. Notice this is almost a spherical bubble, and with only a little bit of the hydrogen bonding here. So now we can also do it where we even change the functional group by moving the oxygen around. In this case here, we're going to start with a carbonyl and a hydrogen on here. Then we can actually, which is of course called an aldehyde. And then we have the carbonyl with two carbons bonding to it, so that's our ketone. But we can also turn it into a ring and just have a cyclic ether, okay? So by changing the functional group, the types of interactions are what change the boiling point with these systems. Okay, so those are constitutional isomers. You can have different functional groups and you can have different properties because of the different available forces. Okay. But now we need to look at the stereoisomers as well. So again, this is a conformational constitutional isomer. Constitutional isomer is when you have different isomers because they're hooked up different ways. Conformational isomers is you're looking at the availability of that sigma bond to rotate, okay? So in the case of this right here, we've actually changed where a chemical bond was. That makes them constitutional isomers. They are different sets of bonds, okay? But they're the same number of atoms, okay? likewise, if we took this right here and just rotated around this axis, notice all the bonds are exactly the same. It's just a different drawing of that same atom. We call those conformational isomers. So that's just how we drew it. It's exactly the same molecule, but it is just how we drew it, that rotation around that signal bond in space. Okay. So now let's move to stereoisomers. Stereoisomers we see them in both things with double bonds when we assign E and C, but we can also see them in things that don't have double bonds, and we'll assign those later as R and S. Okay. Stereoisomers are different compounds that have the same connectivity, except that some part of space has changed. So for example, in this case here, these are stereoisomers because we have on this one, the two chlorines are on that same side, giving us that cis configuration. And our chlorines are on two different sides, okay? And so that gives them our different arrangement of those atoms in space, okay? So technically that also makes these alkenes right here geometric isomers. It's the exact same molecular formula, but again, it's different in space due to the lack of a rotation around that double bond, okay? So we can have geometric and stereoisomers by just their difference in space, okay? So this is both a stereoisomer and a geometric isomer because of that connectivity and that arrangement of atoms in space. Stereo means space. Okay. So we have already talked about E and Z, right? When we were talking about nomenclature, right? So I'm going to go over this pretty quick. We're going to use the exact same prioritization rules for E and Z as we're going to use for the ones that don't have any double bonds. Okay, and our rules are number one, atomic number, not mass, atomic number. Higher the number, the higher priority. If you can't decide just by looking at the atomic number, you look to what's attached to it. And you keep going out further and further until there is a difference, and the one with the higher atomic number wins, okay? And then if you can't decide on that, you also have to go think about if you have a double bond, that'll count to, like a double bond to oxygen counts as 2 oxygens, a double bond or a triple bond to carbon will count as 3 carbons. So that's our third rule for prioritization. Now, when we do E and Z, we only care about one side at a time. So we draw our line in half and we prioritize one side of the double bond first. Then we prioritize the second side of the double bond second and just compare those two. Notice we're only giving a priority of 1 to each side. And that's all we have to do to attain our E and Z. And of course, E is in Gegen, meaning equivalent to trans or across. And Z is zusammen for together. So Z is on the same side. So, okay. And we use those exact same rules we used before. And this is for review if you need to review. Okay. Now, that's because those are fixed in space because of no rotation around that double bond, okay? So that makes them stereoisomers and geometric isomers, and we assign them with that EZ. If you only have 2 groups, you can say cis and trans, but anytime you have more than 2 groups, it's best to use the EZ functionality, okay? Now, what if you don't have any double bonds, okay? That means you're gonna have 4 different things attached to a carbon, okay? So you have in your sp3 hybridized carbons, it always has 4 bonds attached to it, and they're all sigma bonds, okay? So in things with single bonds, we now have what we call chirality, or it's another word for handedness. Chira is handedness. So if we think about it, when we have these things that have free rotation, but we can prove they're fixed in space because of what we call the stereoisomerism. And we can prove stereoisomerism to ourselves by drawing the mirror image of the molecule and then seeing if we can superimpose them on each other. Okay, so what you think about is if you have you know, two hands, then your hands are basically chiral because they are mirror images of each other. If you put your hand up against a mirror, they're mirror images of each other. But when we take them and we try to lay them over so that the index fingers, the wrists, and are lined up, notice that my middle finger and thumb overlap, and my thumb and my middle finger overlap on the other side. So they are not superimposable. The thumbs have swapped places on these two things. That's what we're looking for when we're talking about a chiral molecule. We're looking for when we take the mirror image and put them on top of two of the atoms have switched, the other three atoms will line up, okay? So let's look at that in the slide here. And my slide's still up, right? Because it blinked. I want to make sure. Okay, so first thing we need to do is we need to find what the stereocenter is. And so the stereocenter is usually the carbon or nitrogen that has four things bonded to it, okay? So that's our chiral center, our stereocenter, our chiral carbon. Those are all terms I might use. And it's this one carbon that has those four sigma bonds to it, okay? The first requirement for chirality is to have four different things bonded to that carbon. If you have two hydrogens, a chlorine and a fluorine, the compound is not chiral. It cannot be chiral because you can always rearrange it so all of those molecules will overlap on each other. Okay, so you must have the carbon, usually sometimes it's a nitrogen, in the middle, and four different things bonded to it. Once you have that, now you can start looking at that stereocenter. And the way we look at it is we take one compound here, and we draw the mirror image. The best way I found to draw the mirror image is you draw a line, and then you start from the inside out. And so we're gonna put this bromine here, and you're gonna keep the type of line it is. Notice we have a dashed wedge. That means it's going behind the plane of the iPad or the paper. And the solid wedge means it's coming out at us, okay? So that's sticking out at us. But the bromine, the carbon, and the fluorine here all have straight sticks. They are in the plane of the paper, okay? So now, just with that drawing that way, we now have some three-dimensionality allowed to us, knowing that, oh, that chlorine's sticking at me, the hydrogen's sticking away, and the fluorine, bromine, and carbon are all in the same plane, okay? So now we're gonna draw its mirror image, and we're gonna keep the exact same type of stick or bond we have in the mirror image. So we have a bromine with a stick bond going to a carbon with a stick bond to fluorine. So now we've done the things that are in the plane. Now we have this chlorine sticking out at us. So we are going to do a wedge and put that chlorine sticking out on the other side as well. And then we'll, of course, our farthest away from the mirror is our hydrogen, and it's sticking back. So we draw it sticking back, okay? So now we have successfully taken one of our compounds and drawn the correct mirror image of it, okay? So the other thing we're gonna look at here is there somewhere we can cut through the molecule to where half of the molecule is gonna look like the other half of the molecule? And this is what we call a plane of symmetry, okay? So if we were able to cut through, let's say we made a piece of paper that was cutting through the fluorine, bromine, and carbon here, we would see that the chlorine is on one side, and the mirror image, there's a hydrogen where the mirror image of the chlorine would be. Therefore, that is not symmetrical because it has a chlorine on one and the mirror image has that hydrogen. So we have no plane of symmetry in this molecule. Now, if we did a space-filled kind of stick model here, we can see that they actually cannot line up. In this case right here, we're trying to line up the chlorine and the bromine with each other here, but notice that two of the atoms have swapped places going from this side of the mirror to that side of the mirror. When we swap those two things, that's showing us that we have our chiral compounds, and we have two of them, and they are non-superimposable, but mirror images of each other. Okay, so, all right, so by definition, a molecule is chiral if you can draw its mirror image and they are non-superimposable, then you have two molecules that are different, okay? Because they differ in space. So they are chiral molecules. If you can swap them and show that they can overlap each other, then they are not chiral, or all called achiral carbons, okay? So notice here where when we have two hydrogens on the system here, number one, we have a plane of symmetry because we could actually draw a plane of symmetry in between these right here, and we'd have a hydrogen on this side of the plane and a hydrogen on that side of the plane. So we have a plane of symmetry. So that tells us it's probably not chiral. But then when we draw its mirror image and look at it, we can actually line up all four of the attached atoms on carbon. Okay. If you can line up that material like that or find a plane of symmetry, the compound is no longer chiral and it becomes what we call achiral. Okay. So I'll try to say a chiral carbon versus an achiral molecule. Okay, so be careful that when I say achiral, it's meaning that it is not a chiral compound. Okay. So, and let's dive in a little bit into that plane of symmetry. Like I was talking about, it's sometimes hard to visualize. So when we do it right here, the plane is actually, that we're showing here is in the chlorine, the bromine, and the center carbon. Uh-oh. Whoa. Okay, here we go. There we go. All right. So in this case here, we have the chlorine, the carbon, and the bromine all in the same pound. And you can see that the hydrogen is reflected onto the other side of that plane. And therefore that produces that achiral compound because of our plane of symmetry. Okay, so we have a molecule and we've drawn its mirror image of itself and they don't overlap, okay? So now we have what we call a pair of enantiomers. Enantiomers always come in pairs, okay? And they are only found in compounds with chiral centers, okay? So the key here is that when you find a molecule that has four different things attached to it, okay, that's a good starting point. You draw the mirror image of it, make sure that they don't overlap, and now you've correctly drawn the two different pair enantiomers in that enantiomer pair, okay? So in this case here, we have the fluorochlorobromomethane right here is chiral because no matter how you rearrange these things, and you might want to get a model out and try to prove to yourself that they can't, you're always going to have two of the atoms that won't line up. They'll be swapped with each other. Three of the atoms will always line up. So now that we have these two stereoisomers, and they're a pair of stereoisomers, and we have a special name for it called enantiomers, then we have to make sure that we can identify which is which, okay? So, okay, there we go. So why are knowing these enantiomers important? Well, turns out biological functions are very, very picky about which they'll use one enantiomer or another. And the classical example is this compound right here at the bottom called thalidomide. Thalidomide is used as a sedative. It still is actually used in the sedative in the UK. But what they did was when they made it the first time, they had a mixture of the one compound and the stereoisomer of it. It's an enantiomer of it. The problem is that the body only used the one isomer for calming down nerves and relieving morning sickness. Turns out the other isomer does not have that effect and actually causes it's what we call a teratogen, or it causes birth defects. So you may have heard of the thalidomide babies from the 1960s. That's because of one of the isomers was that teratogen, bad for the human system and not used in the right way. Since then, they've actually reintroduced it in the UK, but although it's not available in the United States, by only synthesizing the one isomer and probably only giving it to men. Okay. The other cool way we can use it is that even though the compounds look the same, by changing the stereoisomer, our body interprets them differently. So the cool thing about this is that we have a compound here known as limonene. Okay, limonene is also used a lot in Gugon. Gugon is actually a mixture of limonenes. And what's cool is that one of the isomers is going to give us that lemon smell. The other one gives an orange smell. And so when you mix them together, they actually have a lemon orange smell. Cool thing is, when you isolate them from plants, the plant usually makes one or the other, but not both, because the biological systems are very specific about their synthesis patterns and will only generate one of the isomers possible. Okay. So now, just because you have, let's look at it. Just because you have a stereocenter in your molecule does not necessarily mean it's going to be chiral. If you only have one stereocenter, the compound is always chiral because there is no way for you to create a mirror plane. However, in the case of these compounds here, we see that this carbon and this carbon are both chiral carbons. And if you want to prove it to yourself, this is a CH2, this is a CCH3, this is a CH3, and then there's a hydrogen back here, don't forget that. So each of those atoms has 4 different things bound to it. So each of these are chiral centers, but if we draw our mirror plane here, the methyl group is going to be mirrored on the other side of it. These other methylenes are going to be mirrored on the other side, making this an achiral molecule. Because we found this plate of mirror symmetry, a compound with 2 stereocenters can occasionally lose its chirality because of this mirror plane. Okay. Let's look at another example of this butane diol right here. If we look at this particular isomer, we have both of the OHs out toward us, the hydrogens back here and the methyl groups up, which means they are perfect mirror images of each other, meaning it has a plane of symmetry cutting straight through that bond. You don't always have to cut through a bond to find that plane of symmetry. Sometimes you actually can cut through an atom, okay? So in the case of this cyclohexane diol, we've actually found our plane of symmetry by cutting all the way through the 2 oxygens here. And so we have the exact same thing on both sides, half of the oxygen on one side, half of the oxygen on the other. And I assume if we drew our hydrogens up here, that half of the hydrogen be on the plane and half the hydrogen be on the other. So even though we have 2 stereocenters and they're kind of far apart, here they're together, here they're 4 bonds apart, that still confines that mirror plane of symmetry, and therefore they become achiral molecules. Non-chiral, achiral, all one word. Okay, so now we know what chiral molecules are, right? It's something with 4 different groups on a carbon, or sometimes nitrogen. And we know that a pair of enantiomers is, if we had one of them, we could draw the mirror image of it and it wouldn't superimpose on it. So that's our pair of enantiomers, right? So now we have chiral carbons and we have our pairs of enantiomers. Now we have to figure out how they're different. Turns out they have the exact same boiling points, exact same melting points. You can't separate them by physical methods like that. You have to do something else. Now, because they are different in space, they are different molecules. And so we need to correctly name them by identifying them. Okay, so the first thing we're going to do is we're going to go ahead and try to come up with a naming system. And the best naming system we have is what we call the R and S naming system, okay? So by using the same prioritization system we use for alkenes, we're going to come up with a way to get our R compound, which is called rectus or right, and then our S compounds, which are called sinister or left, and identify them as one or the other. Okay. So again, we start with prioritization. We prioritize all 4 attached things. Okay. So that's the first thing we have to do. We have to assign all 4 attached things by those 3 rules we have for prioritization. So in this case here, We have an oxygen, a carbon, a hydrogen, and a carbon. So the oxygen is number one priority. It has the highest atomic number 8. Okay. Then we have 2 carbons, both atomic number 6, so we have to go out from there. This has 3 hydrogens on it. This has a carbon and 2 hydrogens on it, making this carbon a higher priority than the methyl group. And then usually hydrogen is almost always 4 because it is atomic number 1, and so it's almost always last. Okay. So now we have our assignment. Our oxygen is 1, our methyl group is 3, our ethyl group is 2, and our hydrogen is 4. Now we're ready to assign R and S. Okay. Now notice they have it drawn in a specific way. They have it drawn where 1 and 3, 1 is sticking out, 2 is sticking down, 3 is sticking back, and 4 is sticking out on the other side. Okay. Some people can actually assign R and S directly from this way it's drawn. But I like to show how to use your hand to do it. It can be either hand, left or right. You just have to follow the same process the whole time. Okay. So let me see. So in their method, when you draw it this way, you're looking for the prioritization. So we're looking to reorient the molecule so that you have your highest priority on the 2 facing out and the 1 in the plane of the paper facing down, but your lowest priority facing back away from you. So see what they did? They rotated this right here. Sorry. They rotated this molecule such that this hydrogen is on the back side here. And when you look at that, you have priority number 1, priority number 2, and priority number 3. That's clockwise. Okay. Clockwise is signified with the R, or right-handedness, rectus. So clockwise gives us the R isomer. If we had it going the other way, where our priority 1 was here, priority 2 was here, and our priority 3 was here, it would be going counterclockwise, and we would call that S, sinister, or counterclockwise. So that's how we'd identify them. Okay. So that's one way to do it. I have another way to do it that I like a little bit better. And so I can actually start from this drawing right here. And what you do is you take your hand and you look at your hand and you're saying, always put your number 4 priority where your wrist is. Okay. So looking at this picture, I would put my hand looking like this because that hydrogen is poking up out of the paper at us. And so I put my wrist up here. And then the next thing that's closest to me is that OH group. So my thumb is going to be priority number 1. The thing that's pointing down, wait, hold on, let's see. Yeah, okay. So then our 3 is going to be my other finger, my index finger here, and my 4, the priority 3 is going to be my index finger, but priority 2 is going to be my middle finger here. Now that I have those priorities in mind, I turn it around to look at it such that my number of priorities behind me, and I go 1, this is 1, this is 2, this is 3, and that gives us clockwise, which gives us our R isomer. Okay. Pick one method or the other and practice, okay? I like the hand method because you can orient your hand any way the molecule is drawn on the paper. You don't have to actually redraw it with a rotation. Okay. So let's try their method one more time here. Again, what we have is we do it where we assign our prioritization. Then we get all 3 of our higher priority groups either facing out at us or in the plane of the paper. And then we look to see which way the priority goes. If the priority is 1, 2, 3, those are going in a clockwise fashion, it is going to be R. If it's going 1, 2, 3, that's going in a counterclockwise fashion, and that is going to be S. Questions on that? Okay. Prioritization rules is the easy part. Orienting this so you can see clockwise and counterclockwise is the Minecraft part. Okay. Okay. So let's try another one here. Okay, so in this case right here, we're doing, we've identified that particular isomer of the butanol as the R isomer, okay? Because we had that where we had our 1, 2, and when we rotated this around, we had our clockwise rotation. Now, let's draw the mirror image of it and then see if it changed. It should be the opposite of the R isomer because it's the mirror image. We should be able to assign it as S. But let's see how we're going to do that first. So the first thing we do, of course, is we draw our mirror plane right here in the middle and start right here. Hydrogen with a wedge, methyl group with a dashed wedge, OH with a solid wedge, and our ethyl group is facing down again, okay? So we now have our true mirror image, okay? Now let's do our assignment here. Our oxygen is going to be 1 again, the methyl group is going to be 3 again, our hydrogen is going to be 4 again, and our ethyl group is 2 again, okay? But we're not ready to do our assignment yet, right? Because our hydrogen is actually facing out at us. So what we need to do is we need to rotate that such that that hydrogen's faced back. And when we do that, our OH comes over here and our methyl group comes out forward. So it looks like this right here, okay? We see that transition. So we see the transition where this hydrogen goes back, this methyl group comes forward, and this OH flips sides to give us that on this position. So now that we've rotated that correctly, now that we have all of our 3 highest priorities on facing us, we can now look to see what order the priorities are in. We have 1, 2, 3, which puts us in the counterclockwise formation. And in the counterclockwise formation, that turns it down to the S. So 3 things. Number 1, we've correctly assigned our thing by looking at the clockwise, counterclockwise. We've correctly assigned our priorities because of our priority rules, and we have correctly been able to translate our mirror image to show what our other enantiomer is. So going back to your enantiomers, it's always a pair of enantiomers. One is always going to be R, the other one's always going to be S. Okay, so when you draw them, they need to be non-superimposable mirror images, and one is going to be R and one is going to be S. Okay, questions on that? Okay, we go to 120? No, huh? 150, right? We have plenty of time. Yeah.
I have a question.
Yes.
Why don't you move the oh, never mind. Okay,
So,
I see.
yeah.
Those downward facing like the CH2, CH3. I thought those would move too, but
No, because you're rotating around that axis. So these are just spinning around and you can't tell the difference. Because you can imagine that this is the axis that you're turning it on to get to the position correctly. Okay. Now, here's where we're going to use the third prioritization rule, which is if you have more than one bond to something, to assign priority. So first of all, we only have one chiral center. It's going to be this one here because it has 1, 2, 3, 4 different things bonded to it, right? And we can assign its priority with that third prioritization rule. So we have nitrogen, which is atomic number 7. So it's going to be our 1. Right here, we have a carbon with an oxygen on it, but we have a carbon and we have 1 oxygen here. Now we have to count this 1 oxygen for the first bond and for the second bond as well. So that carbon has oxygen, oxygen, oxygen on it. This carbon over here has oxygen, hydrogen, hydrogen on it, making this carbon a higher priority. Okay. So even though they both have oxygen bound to it, we had to count all the bonds. And that one has 3 bonds to oxygen, therefore it's the higher priority. And that leaves us at, this is going to be 2, this is going to be 3, and this is going to be 4, okay? So without moving anything, knowing what our assignments are here, 1, 2, 3, 4, can we assign it to be R or S? Okay, so I'm going to use my hand and go 1, 2, 3 and assign it. What do you think it is based on these assignments and our 2 ways of knowing how to assign this? Anybody want to hazard a guess in the chat there? Okay. I think you're right. Okay. So if you want to use your hand, the way you would do that is you orient your hand in this direction here because your hydrogen's already pointing back. My thumb is going to be the one with the OH. My middle finger is going to be the one with the nitrogen on it, and my index finger is going to be the one with the carboxylic acid on it, giving me 1, 2, 3, making it clockwise, making it, oh, no, it's clockwise, it's R, sorry. Now, let's do it the other way. Let's translate this to exactly the way they had it before. So when they had it before, they had the 2 down, and so what we're going to do is we're going to redraw the molecule. We're basically going to tip it upside down. So we're going to draw the carboxylic acid down here. We're going to draw the, so all we're going to do is we're going to rotate this thing 180 degrees. So we have our NH2 over here. Okay, our solid wedge with our OH is still there because all we're doing is rotating 180 degrees in the plane. And our hydrogen is sticking back here, okay? So now we have our 1, we have our 2, we have our 3, and we have our 4. And by looking at it in this direction, we have 1, 2, 3, 4, clockwise, making it R. Okay, so I've shown you both methods for doing that. And so this, this method right here on the paper takes redrawing it to get that orientation correct. You have to have the 2 down and the 4 back to be able to correctly assign the R and S. With your hand, you just have to get it drawn back to looking at it to get your R and your S. 1, 2, 3. Yeah, all right. Questions on that? Okay, so you got 2 different methods. Practice one with the homework, and whichever one works for you, do that. Okay. And this, of course, is how we assigned all of our systems, knowing that each of the bonds counts toward each of the atom attachments. Okay. And that's how we assign. Okay. Now, there's a bunch of different ways to draw these things in 3D space, okay? One of the ways that I like is just the kind of tetrahedral wedge where we have a heavy wedge coming out and a light wedge coming in, but there's no reason you have to do that. Some people like this where the stuff in the plane is here and you have them coming out from them. There's also a third method that actually makes it kind of cool. Let's see. The blue one is S. No, it was R. Yeah, it's R. All right, answering questions. One kind of interesting way to draw it is this right here, okay? Notice nothing's in the plane except for the chiral carbon, the center carbon, right? We have 2 of the groups coming out, 2 of the groups going back, and that makes it kind of interesting to assign your priorities because now you have 1, 2, and 3, and you can assign it that way as well. It's going clockwise. But notice these are all correct drawings of the different isomers possible for this. Okay, so do we have RNS assignment down? Okay, go ahead and practice this. If you don't, go ahead and email me. And again, we're going to have an activity next week, so we get a little bit extra practice. So I said before that these have all the same connections. They're only different in space, and therefore they have the exact same boiling points, melting points, etc. So how do we tell them apart? Okay, well, we tell them apart by what we call optical activity. It turns out that, you know, when these molecules are, all the different forces, van der Waals forces and everything looks about the same, the only way we can tell them apart is how they interact with light. Turns out that light can interact with the component because light has a magnetic component and an electric component. And because of the two different things are swapped in space, they interact with light differently, okay? So if we were to take regular light, which is just kind of scattered all over the place, and we did what we called plane polarized it, okay? So light's a wave, right? And coming out of the sun, they're going in all different directions right here. But what if we filtered out all the ones that weren't in the same plane? And so all of our light was in the same plane coming up and down like this, okay? So if all of our light is in the same plane and we come upon a molecule that is different in space, right? So imagine our plane is hitting the molecule in right where that the three atoms that will always overlap each other are, and it has two different atoms on either side. So that what it's going to do is it's going to interact with that and slightly turn and start turning in one direction or the other. And when it turns in that, we can measure that amount that it's turned, and we can see that we have optical activity, okay? So this is called optical rotation, okay? So all chiral compounds have optical rotation. And the cool thing is that if your R molecule rotates it in one direction, okay, some arbitrary value, your S isomer will rotate it in the equal and opposite direction. Does S always rotate right or left? No. It's random. You can't really predict it easily. But whenever you do have your molecule, or you have your pair of enantiomers, one's going to rotate it one direction, a certain amount, and the other one is going to rotate it the equal and opposite direction. Equal intensity, but opposite direction. Okay. So, and then we use this by measuring it in what we call a polarimeter. A polarimeter is basically you have a cell that's 10 centimeters long, you have a light source and a polarizer, and then you have a filter at the other end. And so the filter at the other end, you want to get it as bright as you can. Then you put your sample in, and then you see how far you have to rotate it to get to that maximum brightness again. That shows you how much the light has rotated over that path length of your system. And that's what we call our optical activity. And those are the numbers we use when we look at this number system. Okay. So if we had just an empty tube or something that is achiral, the light's going to come through exactly the same plane as it was. Okay. The isomer, the pure enantiomer, will rotate it one way or the other. And we call that observed rotation alpha. Okay. Now, if that observed rotation is is clockwise, we call that a positive direction or dextrorotatory. In fact, a lot of biological systems, you'll see a D sugar or an L sugar. That's which direction it rotates its light. Okay. So that's a D or plus is going to be in front of that alpha. And if it rotates it counterclockwise, that's going to give it a negative or levatorotatory. Okay, so we have dextrorotatory, which is going in the positive direction, levarotatory going in the negative direction, positive directions clockwise, negative directions counterclockwise. So Dr. Irvin, if S is counterclockwise, do all S rotate it negative? No, it's completely different. It's an actual measured rotation versus a theoretical assignment. Okay. So whenever we do this, we actually have to know a bunch of things. We need to know the structure of the molecule, the concentration, the length, the wavelength of light. Sometimes the solvent uses even the temperature. The temperature can affect the amount of interaction it has with that system. And so when we do that, we have to be very specific about how we record these things. And so our specific rotation, which is defined what we do for each molecule, taking into account path length, temperature, light, and everything, so that I can compare my results to your results, even though our labs are 2,000 miles apart. Okay, so basically the optical rotation is the observed rotation here divided by the path length that we have. Usually it's 1 decimeter or 10 centimeters by the concentration. And the specific concentration most people use is about 1 gram per 100 milliliters, such that you'll give you the same number. And then when we do that, we also assign our temperature and the wavelength of light right here. So this is our lambda for wavelength of light. This is our temperature it was measured at. And notice now our alpha has brackets around it. That bracket with the temperature and the lambda tells us we have a specific rotation. Okay. Most of the time it's measured somewhere around room temperature, 20 or 25 degrees. Most of the time we use what we call the D line, or the sodium D line, which is about 589 nanometers. And then everything else is can be varied, although we have pretty easy ways to get the correct concentration and the length. Okay. So for an example of that R and S are not equivalent to plus and minus here, we have our R, our rectus, our right, our clockwise rotation in our assignment actually rotates light counterclockwise. And so when we measured it at 20 degrees here and accounted for its concentration in the path length, it ended up with being a negative 23.1 degrees rotation. So it's rotating it counterclockwise that way. The S isomer, if it was pure, is going to rotate it 123.1 degrees also, but it's going to be in the positive direction. And so we're going to say that this is going to be positive here. So we can actually, once we've assigned this, we can actually include that in our name by having it plus S to bromobutane or minus R to bromobutane as well. Okay. Another way it's named, especially in biological systems, is going to be the D or the L. The D is going to be the dextrorotatory or positive rotation. The L is going to be the laborotatory or negative rotation. Okay. So I said we always mark the temperature there because one of the weird things is that as the molecule has enough energy to start doing free rotations around its sigma bonds, it can interact with light differently. So an example is this aminosuccinic acid right here, that at 20 degrees, it rotates light in the counterclockwise direction, but at 100 degrees, it actually rotates light in the clockwise direction, or dextrorotatory. Okay. So it has everything to do with how that molecule is interacting and spinning and whether it's bonding to itself or bonding to other things. That changes how it looks in solution, and therefore it changes its optical activity. By the way, this is the chiral center. Questions on that? All right. So what happens if you mix equal portions of each of them together? The R, does 23 degrees in this direction, the S goes 23 degrees in that direction. If we mix them together, we have what we call a racemic mixture, okay? And a racemic mixture is having equal portions of the R and the S. So the R's are trying all their might to rotate it one direction, and the S's are just rotating it back the other direction as they go through the system. So when we have a racemic mixture, we have zero net optical activity. However, we can use that to our advantage, okay? And that's usually denoted by a mixture of both, is that it's this plus and minus. So it rotates at plus, rotates at minus, and it's not optically active. Or else we have, and this is easier than writing R and S. You don't have to write 50% R, 50% S 2-butanol. You can just write this plus and minus 2-butanol to give us that. So, but we can use this to our advantage to see if there's one in excess of the other. Okay. And so what we're going to talk about that is that we can tell if it's not an equimolar mixture. That means we will have optical activity. Okay. So let's say we only have some of the R and more of the S. Okay. So it's going to rotate more of the light. Less of the light is going to be canceled out by the other isomer, and we will actually see optical activity. And by comparing the optical activity of that mixture to the optical activity of the pure, we can see how much more of the other compound we have. And that's what we call enantiomeric excess. Remember, they're enantiomers. One of them we have more of. So it's enantiomeric excess, or EE. Okay? And we can calculate that from the optical rotation. Okay? So we can also calculate from the and we can use that optical rotation difference to calculate the number of moles of one or the other. Okay, so if we look at this first equation here, and it's probably one of the few times we're going to use a calculator in organic chemistry, but we have our observed optical rotation divided by our specific optical rotation of the pure enantiomer times 100. And so it's in a percentage here, okay? So what does that look like? Okay, so the weird thing is that it's not going to be, oh, I have a 50-50 mixture, I have 0 rotation. I have 10% of the impurity, so it's going to be 90% of the optical rotation. No, because we have 10% rotating it one way, and then it cancels out 10% of it rotating the other way, which means we're only measuring the remaining 80% is the one that actually is doing it. So the calculation seems a little funny, but let's go through a couple different examples to show you that it's all about how much was excess that's giving us that rotation. The ones that are the 10% cancels out 10%, and then whatever's left over does the rotation, okay? So that's why it's always called enantiomeric excess. So if we had 100% of the butanol right here, we know that it's going to rotate light in a positive direction, and it's going to rotate the positive direction 13.56 degrees. And if we don't have any of the other isomer, if we don't have any of the R isomer in this, we have 0 rotation to the negative side, and we have 100% rotation to the positive side. That means we have our pure system. Okay, now, what if we add 3 equivalents of our other isomer, our R isomer? Okay, those 3 equivalents are going to cancel out 3 equivalents of that, leaving only, what is this, 14 of the 20 available to us, and therefore it's going to give us a lower number. Our measured rotation is only 9.4. So that's about 70% of the rotation we would normally see. And what that calculates out to on a mole basis is it's 85% the S isomer and 15% the R isomer. But our measured optical activity is only 70%. And that's because those have to be canceled out before and only the remaining set rotates the light. So let's do that again. Let's add another, let's get it to about 75 physical percent, mole percent right here. And what we see is our optical rotation drops down to 50%, okay? Oh, the 13.52 is the optical rotation of the pure isomer, okay? So when at this point right here, once we have it at 50%, all of these cancel out. And so we only get 50% of optical activity available to us, but we have 75 mole percent of our original material and 25% of our other material. And so we see our measured optical rotation drops down to 6, which is about half. And then of course, if they're all canceling each other out, we have 0 optical rotation, and we have our racemic mixture. Now, let's do the other isomer. We're actually starting with a negative number here, and by adding a little bit of that material, getting up to that 70% of the optical activity, we actually have 5 mole percent of the one that rotates it into the counterclockwise position, or the R isomer. And we only have 15% that's going to shift it that way. And then of course, when we go to the 50% optical activity, because all of these cancel out, we're actually looking at 25 mole percent of our impurity, 75 mole percent of our pure compound. Okay, so we can always calculate the percentages from the optical rotation and the optical rotation from the percentages. Questions on that?
Would the specific rotation of the pure enantiomer be provided?
Yes. Yeah, you have to have that pure one to be able to do the calculation. So you get the pure optical rotation and a measured optical rotation, and you can back calculate the percentage. Okay. All right. So that is things with just one stereocenter. Okay. With one stereocenter, you always have enantiomers. You never have a mirror plane. It's pretty easy to figure this out. Okay. Now, if you have two stereocenters, things get a little more complicated. Because number one, you have to assign your R and S to each of the stereocenters, but you also have a new type of material right here. So the number of isomers possible is actually almost exponential right here. So in the case of any type of compound, if you have two stereocenters, it's going to be 2 to the 2. If you have 3 stereocenters, it's going to be 2 to the 3. If you have 4 stereocenters, it's going to be 2 to the 4. Okay, so things get complicated very fast when you have stereocenters. So in the case of 2 stereocenters, you can have 4 different isomers available to you. In 3 stereocenters, you're going to have 8 possible isomers. And in 4 stereocenters, you're going to have 16 possible isomers. Okay. Now, how do you figure that out? Well, we start with our first pair of enantiomers, and then we work out from there. Okay. So.
Hey, I have a question.
Yeah. Go ahead.
Okay, I just figured it out. Thank you, sorry.
Okay, great. Okay. So the first thing we do is we take our molecule that has 2 stereocenters and we draw its enantiomer. And we draw its enantiomer by drawing a mirror plane and starting from the inside and coming out. So we have methyl groups match, hydrogens match, bromines match, and these match. Notice our configuration is slightly different. We have this particular diagram, which is called a Fischer projection. I think it's a Fischer projection. I'm drawing a blank for some reason right here. So in this configuration, the first thing we have to figure out is how these things are oriented right here. So in this kind of configuration, all of the things pointing out away, oops. Okay, let me do this. All the things that are pointing laterally are coming up out of the page, okay? So those are all coming up out of the page. So if we want to assign R and S, we'll know exactly where they are, okay? The ones that are going up and down are either in the plane of the page for the center 2 carbons or behind the center of the page, okay? So that's the first most important thing about our projection here, okay? Now that we have our projection and we want to go ahead and, so what I'm going to do is on this side, I'm actually going to draw these as wedges to reinforce the idea that these are coming out at us. But see how it's easier just to draw it as everybody draws in that same configuration, it's going to be done. And then these are going to be dashed wedges here. So the first thing we do to make sure we have our pair of enantiomers, remember our pair of enantiomers have to be mirror images of each other and non-superimposable. We get that by drawing our mirror image and getting our groups to line up like this. So now this is a pair of enantiomers. So that's our first set of stereoisomers we get when we have 2 or more stereocenters. However, to get the next set of stereocenters, we can't just draw a mirror plane because we already had that molecule. So what we're going to do is we're going to swap one of the stereocenters on one of those isomers and draw that compound. So in this case here, we have swapped these 2 atoms to give us our first isomer, okay? Once we have that first one swapped, now we do our mirror image again, and we can generate this. And now you're sitting there, oh, wait, hold it, there's a mirror plane. If I draw a mirror plane here, no, there's a methyl group down here and a methyl group here. No mirror plane yet, okay? Okay, we're gonna look for mirror planes, but we don't have one yet. Okay, so that's how we go from our first set of enantiomers that are mirror images of each other to start our second set of enantiomers that we have. Now that we have our one drawn here, we do our mirror plane thing, draw it again. Okay, so now we have all 4 possible isomers of this compound because we had 2 stereocenters. Okay, and what we're going to see here is that our, let's see, when we assign this to, when we assign these, the number 2 position here is going to be R, and this one's going to be R as well. And which means in our mirror image, both of those are going to turn into S, S, and S. So that's our first pair of enantiomers, RR, SS. Okay. So when we actually assign them to the second one, we're going to see that's changed now. We're actually going to end up with, oops. There we go. This one is going to be S. This one, this number 2 carbon is going to be S, but this is going to be R. And the cool thing is, because our mirror image, we now know that this has to be an R and this has to be an S. Okay. So that's how we got to having those 2 sets. Notice one is, they're both the same assignment over here. They're both R, and then the mirror image is both S. And then we had to swap one of them to get to the other set of isomers. And these are obviously separate isomers because this is an S and an R, and this one's an R and an S. Do we see how we have now 4 unique isomers of these compounds? Okay. So now that we have 4, interestingly, we have another thing, another definition here. We now have what we call diastereomers. Okay. So diastereomers, unlike enantiomers, do not have to be mirror images of the different sets. Okay. You have a pair of enantiomers and you have a pair of enantiomers, and those 2 sets of enantiomers become the set of diastereomers. Okay. Enantiomers always come in pairs. Diastereomers are 2 sets or more, because if you had 3 stereocenters, you're going to have 8 isomers. And if you had 4 stereocenters, you're going to have 16 isomers. Okay. But now we also have to pay attention to, is there a mirror plane available to us in any of the mirror images? Okay. So let's do that again. Okay. The cool thing is that once you have 2 stereocenters, the pair of enantiomers are going to have the same physical properties. This pair of enantiomers are going to have the same physical properties, but the 2 sets of enantiomers can have different physical properties because they're no longer mirror images and superimposable. So we can actually have different melting points, different boiling points on these materials. All right. So another way to look at it is, if we took this right here and we put it in there as a mirror image of itself, right here, we draw it right here, and we did this and drew a mirror image of itself, we have our set of enantiomer here and set of our enantiomer here. Now, if we had just one from each set, that would be a pair, that would be a set of diastereomers, because they are not enantiomers. Notice that these are opposite each other here. They are not the same, but they are stereoisomers, and the stereoisomer, specifically, they are called diastereomers. Okay. We're getting close to 150. Okay, and they are Fischer projections. Okay, good. All right, let's pick up here on Monday. I'm going to pick up with this nomenclature on RNS. Okay. All right, thank you. Go ahead and practice one of those 2 ways of looking for your system, either this written down method that we're going to do tomorrow or the hand method. Whichever works for you, use it. Okay. All right, I'm going to stop recording and stop sharing. And if you want to stay behind and ask questions, go ahead, please.